mute.
Great.
Good afternoon here in Mexico.
I leave you the floor, Hugo.
Thank you, Jose. So we have, we're going to start this second session about control system. And I saw that we have the author of paper number 3. Talking around. Please, if you can open your microphone and share your screen. The author of paper number 3, yes, is here.
We can see him online.
Yes,
but,
he's connected, but I don't know what happened. What's going on? The Marina, are you in the session? Okay, we wait 2 minutes more, and if he does not show, we play the video.
Yes.
I think that Yuki, you have the video already.
Okay, there we are, but we cannot hear you. You seem to be talking, but we cannot hear you. Can you hear him, Hugo?
No.
No, there is something with your microphone.
Probably it would be better if we play the video.
Yes, it is 4 minutes now. So,
yes.
Oh, okay. Please go ahead. No, we cannot hear you. We cannot hear you. So it seems to be that there is an issue with your microphone. If the authors don't mind, we could play the video, and then you could be in the session in question time if we have some time left. Okay. Oh, this is Oyuki's screen. So, but there is no audio, Oyuki.
Welcome everyone. This is Hector Marina speaking, and I am going to talk about how to use different guided vector fields in our Paparazzi autopilot. This is a joint work with my colleagues Murat and Gauthier from France, from ENAC, and me from the Universidad Complutense of Madrid. And all of us, we belong to the open source project for autopilots called Paparazzi. This logo over here. Let me motivate this technical talk. So why do we care about guidance systems? In Paparazzi, our guidance systems provides path tracking for our aerial vehicles. For example, consider that you have a vehicle and you want to travel from A to B, and you really care about how you do it. For example, just you want to follow a straight line, or you fancy a more complicated trajectory such as sinusoidal. Why not? Or maybe you just don't want just to travel from A to B, but you want just to survey. considering A and B, for example, just by making an ellipse. So our guidance system must make the vehicle to follow such a path, and simultaneously it has to handle the possible complex dynamics of your vehicle, not only just a free particle, but it could be like a fixed wing aircraft. In Paparazzi, we have two guidance systems based on guiding vector fields. The first one, and I'm going to talk about it in the next slide, is based on tracking level sets of the desired path. We are going to see one way. The point here is that it is very few, so there is only one game, and you can codify simple trajectories. By simple, I mean, for example, non-self-intersected paths. So you can codify polynomials such as splines, trigonometric functions, sinusoidals, etc. And we have a second guiding vector field that is an extension of the first one, but it can handle more elaborated trajectories, that they are based on parametric equations. However, it's a little bit more difficult to tune, so you have more gains, but it only requires maybe one or two flight tests, no more. Once you know the dynamics of your vehicle, it's quite easy to tune, I would say. And the point here is that we can handle more complex two-dimensional trajectories, such as eighth figures, for example, which is self-intersected, and even 3D trajectories at the same time that we are handling complex dynamics, such as the ones from the fixed wing aircraft. Let's start with the first guiding vector field, which exploits level sets of the trajectory path that is desired to follow as a guiding system. So let's consider that we want just to track a circle. So here is the implicit equation of the circle, and every time I substitute the x and y position of my vehicle here, if I evaluate it in this expression, if it is bigger than 0, means that I am outside of the circle, less than 0, I am inside the circle, and if it is equal to 0, means that I am exactly on the circle. Okay, so we use this expression just to get a notion of error, if I am outside, inside, or on the circle. No? So we have some sort of left and right. So we take the circle, and if we took the tangential vectors around the circle, every single level set will just be parallel to the target circle. If we combine it with the orthogonal of these vectors, then we can go through the circle if we are outside or inside. And this is the information that we obtain from evaluating in the implicit equation of the circle. So both vector fields, tangential and orthogonal, makes as a result this guiding vector field that is taking our vehicle and it's guiding it. So it's telling, hey, you have to follow this velocity vector in order just to converge to the desired path. So what is the information that you need to pass to Paparazzi? Okay, first, let's say on the blackboard, what you need is just to agree on what is going to be the implicit equation of your path. For example, this is the one for the circle, as we have seen. Secondly, you perform the gradient just to create these tangential and orthogonal vectors. So the first term will be just the partial derivative with respect x, and the second term partial derivative with respect y. And thirdly, we need a Hessian, which accounts for the curvature of this path. So we can pass this information to handle the complex dynamics of a fixed wing aircraft, for example. In this case, it will be partial derivative of x, so 2, partial derivative of y, 0, and the same one. So because it's a circle, it has always the same curvature. In this case, is just equals. Now that we have computed on the paper all this information, we need to codify it in Paparazzi. And the point here is that it's extremely easy to do. We have created an architecture for this guiding vector field and guidance system that you only need to provide in a single C function such information. For example, we call it just GDF circle info. First, we need the vehicle's position just to evaluate the level set that is here. So this is the implicit equation of the circle, and also serves us to calculate the level set. So it's here. So phi is equals to. Secondly, the gradient. So we have a structure gradient. So you provide what is nx and ny, nx and ny. And thirdly, the Hessian. That's it. You don't need to do anything else. The only thing that you have to do one extra step, that is to create this C function that you are going to call from our flight plan. Okay, so once you have your vehicle flying, you have to call it in order to track this circle. And in the end, what you are doing in this function that you have to create, it's only just to tell the function, okay, what is the information about the circle that you already computed? Secondly, this gain that is going to tune how aggressive is going to be the guiding vector field. And thirdly, you pass to the algorithm that is completely transparent for the user such information. So the parameters of the circle, the gradient, and the Hessian. Here we just have a slide to show the performance from a real flight. This is the telemetry from a real flight. So we have a fixed wing aircraft here pointing in this direction, traveling in this other direction with a black arrow, and how our controller makes the vehicle to align the velocity vector with the guiding vector field. So eventually it converges to other side ellipse. In fact, there are two ellipses. So once the guy is after 2 or 3 turns, it jumps to another ellipse here. So not too bad. And here we also account for the wind. Let's jump into the second guiding vector field, which can handle parametric equations as description of the desired path to be tracked. Again, if we look at the circle, here everybody would agree that if we substitute different values for W, eventually X and Y will describe a circle. This guiding vector field works by considering this W as a third extra dimension. So we have X first dimension, Y horizontal and vertical, for example, and here W is a third dimension. So this is not just a circle; it's some sort of a spiral. So for W equals 1, we see how much X and Y is the value of X and Y. For 0, 5, maybe it's here. For 0, it's there. So in the end, we have a 3-dimensional object, not just a 2-dimensional object. If we look at the projection, of course, in the end, we have a circle. And what we have to do is something very similar as in the first guiding vector field. We compute the vectors which are tangent in this 3-dimensional space to this new 3-dimensional trajectory, and we also compute what are the orthogonal vectors, and the combination of both will guide our vehicle to this 3-dimensional trajectory. Of course, one of the coordinates is visual, so this is just computed in software, but X and Y are physical. So if we converge to this 3-dimensional path, physically, we also converge to the 2-dimensional circle. And those are the error vectors that we are, the error signals that we are calculating. So for X, R cosine of W, and we compare it with the actual position in X of our vehicle and the same from Y. And we are going to start from these two signals to compute partial derivatives in order to pass this information to our control. Here we have an example of how to implement a trajectory using this second guiding vector with parametric equations. In particular, we are going to implement a circle that is tilted in the 3-dimensional space. So its projection is an ellipse in the 2-dimensional space, but in the end, it's just a 3D circle, let's say. So as a user, you only have to provide a C function that you can copy and paste, and you only have to, let's say, substitute in the template these 9 pieces of information. So the first 3 ones are the 3 parametric equations. So for the circle is X and Y, okay? So it's the offset of the waypoint and R cosine, R sine. Nothing more difficult than that. And for the third one, here we take into account what is the maximum and minimum altitude for tilting this circle. And the rest of information is just the partial derivatives with respect to W. So here, the partial derivative of R cosine will be minus R sine. For the R sine will be R cosine, and so on. And here, the second partial derivative is just to account again for the curvature, for handling the complex dynamics of your vehicle. So you have to compute the partial derivative with respect to B of these 3 expressions. finally, we can exploit these two guiding vector fields to synchronize different vehicles on the same path. The notion that I am going just to debrief here is that if each vehicle, for example, for the circle, has its own W1, and the second vehicle has W2, we can apply what in control we call consensus algorithms in order to specify what is the distance between W1 and W2. For example, if 3 vehicles have the same W, that means that they are going to converge to the same position within the path. If we, for example, put them in the circle by radians away, so that means that they are going to be in the same path, but they are going the farthest position as possible. So they will be, let's say, in opposite directions into the circle. And finally, our future work. So all the things that I have explained already, they are implemented in Paparazzi, both the multi-vehicle and the first and the second guided vector field. And there is still work to do here. So far, our guiding vector field only supports fixed-wing aircraft, mainly because it's me who is using it and I am flying aircraft. So if there are people interested in porting this to other dynamics, such as rotorcraft or rovers, so you are very welcome to contact us and let's see how we can implement it. It's not so difficult. In the end, all the algorithms are implemented already. It's just we have to do minor modifications into the firmware of the rotorcraft and the rover. So that's it. Thanks a lot for your attention, and I will be very happy to answer to any questions you may have.
Hector, are you in the session? I think that the author is not in the session. Okay, so we have to continue. We continue with the next paper is Immersion and Invariance based trajectory tracking control of an aerial manipulation system. And I think that the author is here. Please, Aaron, do you want to share your screen to be ready to start in less than a minute?
Hi, can you hear me?
Yes.
The sound is good?
Yes, the sound is good. And
perfect.
Just need, please share your screen.
Okay.
Okay, let's wait for 1 minute to start at 6:20.
Can I start now?
Okay, yes, let's start.
Okay, thank you. Hello, everyone. I am Aaron Lopez. I will present you the research work entitled Immersion and Invariance-Based Trajectory Tracking Control of an Aerial Manipulation System. This work was developed with the supervision of Hugo Rodriguez, Israel Cruz, and Jose Martinez. The presentation is organized as follows. First, I will present the purpose of this research and the goals. Next, I will present the previous work of this research. After that, I will describe the position control strategy based on the immersion and invariance theory developed for this research. Then, the experimental setup and the results will be discussed. Finally, I will present the conclusion and future work of this current work. The number of applications in which aerial robots or UAVs are used has grown rapidly over the recent years. Aerial manipulators are designed to perform physical interaction with the surrounding environment. However, technological challenges still need to be addressed before reliable use of such technology becomes possible. Among these challenges, the capability to carry on a manipulator and handle disturbances during the movement of the manipulator is still a difficult challenge for small-sized UAVs. A small-sized quadrotor is capable of loading a lightweight manipulator and maintain a stable flight with a proper control algorithm. The quadrotor is a nonlinear, open-loop, unstable, and underactuated system, and the incorporation of a moving robotic arm to the structure increases the disturbance to the system that cannot be easily eliminated by the feedback controllers. In order to tackle such problems and to improve the system performance, researchers had proposed a host of advanced control methods to guarantee a stable flight during the manipulation task. The immersion and invariance method is a methodology to design direct and indirect adaptive controllers for nonlinear systems. The immersion and invariance approach captures the desired behavior of the system to be controlled by introducing a target dynamical system. Then, a suitable stabilizing control law is designed to guarantee that the controlled system asymptotically behaves like the target system. The purpose of this research work is to update the internal commercial quadrotor controller with an external immersion and invariance adaptive control loop to solve the position control problem of an aerial manipulator. At the beginning of the research, we developed an aerial manipulator based on a commercial UAV Bebop2 with a 2-degree of freedom arm and extension legs to put the arm in the lower part of the structure to study the behavior of the system with the added weight and the disturbance of the arm. The manipulator was designed and implemented based on the technical capabilities of the selected aerial platform. Then, when a stable flight was achieved through a computational compensation control, we improved the capabilities of the proposed aerial manipulator, implementing an external control loop based on a gain schedule PID control strategy to work with the internal Bebop2 controller and mitigate the disturbance induced by the movement of the 2-degree of freedom arm and the contact with a vertical surface. For this work, we combined the estimation pose technique based on the Visualislam approach with our area manipulation system to extend its capabilities to outdoor scenarios where the use of caption motion systems to sensing the pose of the vehicle are limited. To improve the results of previous work, we considered the implementation of the immersion and invariance approach as an alternative to the gain schedule PID external control due to capabilities to increase the robustness of a nonlinear system against disturbances. Before explaining the implementation of the research, I recall the fundamental condition for the standard immersion and invariance controller design. Consider the system expressed in equation 1 and the target system expressed by equation 2. The immersion condition is defined by equation 3 and by equation 4. The system of equation 5 with the state set has a globally asymptotically stable equilibrium at 0 uniformly in X. Given the system 1 and the target dynamical system 2, find is possible a manifold M described in parametric form by equation 3, which can be rendered invariant and asymptotically stable, and such that the restriction of the closed loop system to M is described by equation 2. Notice that we design a control law U that drives to 0 of the manifold coordinate set and keeps the system's trajectory bounded. Aerial vehicles' internal autopilot shape the system response at different levels depending on the available sensors. Hence, if rotational states are measured, the internal autopilot can shape the aerial vehicle response as a second-order system. If, in addition, the translational states are measured, the aerial vehicle can command to behave as a first-order system. We can assume that our area manipulation system can be represented by equation 7. The proposed controller is expressed by equation 8. Thanks to the quadrotor symmetry, the controllers for the X and Y position are designed following exactly the same procedure. To validate the assumption that our proposed area manipulator can be modeled as a first or second order system, a set of tests were developed to investigate the response of the system to an input signal. First, the quadrotor was tested to prove that the internal controllers work efficiently. Then we repeat the experiment with the same signal, but now with the robotic arm attached to the quadrotor to compare the influence of the robotic arm in the system. The figure shows the sequence of movement the system performs in each experiment when the input signal is sent to the vehicle. Several tests were carried out to obtain a mean result of the behavior of the system in both experiments. The graphics of this figure show the most representative result in the first experiment. The results of the second experiment are also shown in the figure. As in the first experiment, a set of tests were carried out. According to the results shown in the graphics, we prove the system behaves as a first-order system even with the robotic arm attached to the structure. Therefore, we can assume that our proposed area manipulator can be described by equation 7. The proposed control strategy was proved via experimental tests in an outdoor environment. We incorporate the Visualislam technique. This method takes advantage of two characteristics of the aerial vehicle, the onboard camera and the attitude measurement. The control algorithm runs in a ground station, and we take advantage of the Wi-Fi and Bluetooth connection to communicate the computer with the robotic arm and the quadrotor. The coordinate frame of the area manipulator is presented by the figure. The longitudinal and lateral motion of the systems are represented by the X and the Z axis. The immersion and invariance controller was implemented for both axes. A standard PID controller was also incorporated to control theta and Y axis and guarantee the correct orientation and distance to the ground. The outdoor scenario can be shown in the figure. In this research work, we decide to put a robotic arm on the top of the vehicle. This allows the sensor below Vivo 2 to operate without any kind of obstruction and guarantee a good measurement. This change in the position of the robotic arm also reduces the load because the extension legs are no more needed. The carpet below the area manipulator provides visual features which ensures a good performance of the pose estimation method and reduce the pose estimation error. The pose of the system when it's in flight mode is provided for the Visualislam technique. The movement of the robotic arm to fall and unfold produce a set of different disturbances. The objective of the attitude control is to reduce the displacement produced by this disturbance and any other disturbance induced by the outside condition to maintain the aerial vehicle in the desired position. The proposed controller operates as external control, calculating the control signal U for the X and Z axis to display the vehicle to the desired position. Then, the U signals are sent to the internal control of the quadrotor. Finally, the pose estimation provided by the Visualislam closes the external control loop. Through several experimental tests, we study the behavior of the system and tune the parameters of the control law. The graphic shows the response of the system in the first experiment when the value of the parameters was chosen according to our experience. Due to facility provided by the immersion and invariance technique, after a few experiments, we are able to tune the value of the parameters and ensure the system reached the desired position and maintain the pose during the disturbance induced by the environment and the robotic arm. The graphic shows the results of the final experiment. Let me show you a video of the experiment where the difference between a standard PID control and our proposed controller is presented. In this work, a control strategy based on immersion and invariance technique has been designed and implemented in order to control an area manipulator to tackle the issues related to the environment and the movement of the robotic arm. The experimental results obtained for several tests are quite promising. A merit of the proposed algorithm is shown by the equation of the control law, which reduces the number of parameters of the controller, simplifying the experimental phase and allowing to obtain an efficient performance of the system. According to the results obtained in this work, we consider that the control can be tested near to a vertical surface and aiming to make contact with the end effector of the arm. This could represent a novel approach for our aerial interaction field. Thank you very much for your attention.
Thank you, Aaron. We have time for some questions. Do you have questions? We have a question is, can you extend the method to also deal with unknown reaction forces or loads?
Sorry, can you repeat me the question, please?
Can you extend the method to deal with unknown reaction forces?
Yes, actually, the forces of the arm and the environment were not these forces we don't measure these forces. So yes, we can extend the other forces that cannot measure for implemented this control law.